Hi everyone. In the previous lectures, we've learned that if you're studying a dynamical system or differential equation that comes from a matrix, then a good way to understand the system is to diagonalize the matrix. And in order to do that, you need eigenvalues and eigenvectors. In this lecture, we're going to talk about how to find the eigenvalues and the eigenvectors of a matrix. But first, it would be good to have a geometric interpretation of eigenvectors. So remember that the equation that describes eigenvectors and eigenvalues is this equation, a times v equals lambda times v. And remember that in order to count as an eigenvector, the v needs to be a non-zero vector that satisfies this equation. The lambda can be anything, including 0, but the v has to be a non-zero vector. So let's draw a picture of this situation. Here's a vector v. Now because v is a non-zero vector, it's going to span a one-dimensional subspace, or in other words, a line through the origin. Now the equation av equals lambda v says that when you multiply v by a, you get a scalar multiple of v. And so that means that the result is another vector on the same line. It might be pointing in the same direction, it might be pointing in the opposite direction, it might be longer, it might be shorter, it could even be the zero vector, but it's somewhere on that line. Now suppose we have another vector on this same line. Now, since that vector is on the line that's spanned by v, it's going to be a scalar multiple of v. So it's k times v for some k. Well, what happens when you multiply that by a? Well, a is linear, so you can pull the scalar k out, and so that means you get k times av, which is k times lambda v, and you can rewrite that as lambda times kv. And so this tells us that k times v is also an eigenvector with the same eigenvalue lambda. So what this means is that you never just have one eigenvector. You actually get an entire line of eigenvectors. And it's the line that really matters. What's happening is that when you multiply by a, that line is getting scaled by lambda. So if lambda is bigger than 1, then the line is getting stretched out. If lambda is less than 1 but positive, then the line is getting squashed. If lambda is negative, then the line is getting flipped. And if lambda is 0, then the entire line is just getting squashed down to the 0 vector. When you solve for eigenvectors, you're really looking for these lines. But the eigenvector is just a nice way of representing that line. It's a basis vector for the line. All right, so back to the question of how to find eigenvalues and eigenvectors. So just to remind you of the problem, given an n by n matrix A, we want to find a scalar lambda and a non-zero vector v such that a times v equals lambda times v. Now what's tricky about this is that there isn't just one thing we're trying to solve for, there are two things. There's the lambda and the v. That, together with the fact that the equation is kind of simple looking, makes you feel like you just don't even know where to start. But there's a trick. So the first thing that's weird about the eigenvalue equation is that the left side involves a matrix and the right side doesn't. So one way to fix that is that you can rewrite the right-hand side as lambda times the identity matrix times v. Now you've got a matrix on the right-hand side. And now you can move that over to the left, and you get av minus lambda iv equals 0. And when you factor the v out, you get the equation a minus lambda I times v equals 0. And when we write the equation this way, it brings it much, much closer to things that we're already familiar with. This equation says that v is in the kernel of a minus lambda I. And furthermore, since v is supposed to be non-zero, it's a non-trivial element of the kernel of a minus lambda I. And what's useful about that is that some matrices have non-trivial kernels and some don't. And so this allows us to break the problem up into two parts. The first step is to find values of lambda such that a minus lambda I has a non-trivial kernel. And then the second step is for each such lambda, we need to find vectors in the kernel. And the cool thing is, you already know how to do these steps. You might not feel like it yet, but you do. For step 1, the key observation is because we're dealing with square matrices, we can compute the determinant. And the determinant tells us whether the matrix is invertible or not. If the matrix is invertible, then the kernel is trivial. And if the matrix is not invertible, then the kernel is non-trivial. So that means we can calculate the determinant. And when the determinant is non-zero is exactly when there's a non-trivial kernel. Now this is a little weird because lambda is undetermined, but the idea is that you can actually compute the determinant with lambda as being undetermined. And then what you end up with is an equation in lambda where you can actually solve for lambda. And that's how you find the eigenvalues. And then once you find the eigenvalues, you plug in the values of lambda, and then you can solve for the kernel in the same way that we've done since the beginning of the semester. Okay, so now we're ready to actually describe the steps that you would do to find the eigenvalues and eigenvectors. Step 1 is you compute the determinant of a minus lambda I, with lambda being treated as a variable. It turns out that whenever you do this, the result is a polynomial in the variable lambda. This polynomial is called the characteristic polynomial of A. And the next step is that you factor the characteristic polynomial, and the roots are going to be the eigenvalues. Those are exactly the values of lambda, where the determinant of a minus lambda I is 0, and so the kernel of a minus lambda I is non-trivial. And then finally, for each eigenvalue lambda, you plug it in to calculate a minus lambda I, and then you solve for a minus lambda I times v is equal to 0. The non-zero solutions are the eigenvectors, but this is a kernel, so it's a subspace. If there are non-zero elements, then there are going to be an infinite number of eigenvectors. Sometimes it's convenient to talk about that entire space of solutions, and that's called the lambda eigenspace. But usually, for practical purposes, you're just going to find a basis for this subspace. But this is something that you know how to do already, because this is just finding the basis of a kernel. So let's look at a basic example. Suppose we want to find eigenvalues and eigenvectors of this matrix. So the first thing I'll do is I'll just write out a minus lambda I. Now lambda times I just has lambdas down the diagonal and zeros everywhere else. And so what you get is something that looks like A, except it has minus lambdas on all of the entries on the diagonal. So then the next thing we want to do is compute the determinant of this. And so that's going to be 1 minus lambda times 4 minus lambda, and then minus 2 times 1, so that's a plus 2. And so when you expand out the parentheses here, you get lambda squared minus 5 lambda plus 4, and then there's still that plus 2 there. And so that's lambda squared minus 5 lambda plus 6. Obviously, feel free to skip some of these steps if you feel comfortable doing so. And so we want to find the roots of this polynomial, so we'll try to factor it. And in this case, you can factor it by hand. It's lambda minus 2 times lambda minus 3. And so from that, you can see that the eigenvalues, the roots, are lambda equals 2 and lambda equals 3. So then what we want to do is go through each of these eigenvalues one at a time. Plug them in to a minus lambda I, and then find the kernel. So for lambda equals 2, we want to look at a minus 2i. And actually, you'll notice here that the matrix we ended up with has rows and columns that are multiples of each other. That's to be expected because we chose the eigenvalues so that we would get something where there was a non-trivial kernel. And that only happens when the rows and columns are linearly dependent. And so in the 2 by 2 case, that really does mean that the rows are multiples of each other and the columns are multiples of each other. And so if that doesn't happen, that's a good sign that you did something wrong in computing your characteristic polynomial or factoring it. So anyway, to get the eigenvectors, you solve for the kernel. So to do that, you put it into reduced echelon form, and this is what you get. So there's just one equation, x1 plus 2x2 equals 0. And in this case, we would treat x2 as a free variable. So if you want, you could substitute in a parameter, but I'll just leave it as x2. And so x1 is equal to minus 2x2, and so you can use that to get your solution for x. And then, like always happens when you're solving for a kernel, you can represent your solution as a linear combination of basis vectors. And in this case, there's just one basis vector. It's minus 2, 1. And that basis vector is the eigenvector that you're looking for. Okay, so next we need to do exactly the same thing for lambda equals 3. I won't spend a lot of time on it because it's exactly the same steps with different numbers, but here are the calculations in case you want to pause and check. The key point is that you get the eigenvector minus 1, 1. And then I'll point out that with this information that we found, we can diagonalize A. And all of the information for that is right here in front of us. We just set P to be the matrix whose columns are the eigenvectors. And we set D to be the diagonal matrix whose diagonal entries are the eigenvalues. And that's it. It will be true that P inverse AP is equal to D. You can check it if you want. So this example illustrates the general idea of the process, but in practice there are subtleties that can appear depending on what the matrix is. So I want to show you a few more examples so you can see some of those subtleties. So here's an example. Let's suppose we want to find the eigenvalues of this matrix. This is actually a pretty interesting matrix because the dynamical system that's associated to it is related to the Fibonacci sequence. So this is something that we'll talk about a little bit later. For now, let's just calculate the eigenvalues. Well, the process for that is the same as before. You want to calculate the determinant of A minus lambda I. So that's going to be 1 minus lambda times minus lambda, and then minus 1. And when you expand the parentheses, you get lambda squared minus lambda minus 1. So in this case, you could try to factor the quadratic by hand, and you're not going to be able to do it. But you can use the quadratic formula. And so when you use the quadratic formula, you get that lambda is 1 plus or minus the square root of 1 plus 4 divided by 2. And so that's 1 plus or minus square root of 5 over 2. So those are the eigenvalues. They're irrational numbers, but there's nothing wrong with that. So the moral of the story here is that you can use the quadratic formula, and sometimes that's what you have to do. All right, so here's another example. Let's suppose we want to find the eigenvalues of this matrix. So again, it's the same process. You compute the determinant of A minus lambda I, and in this case you get 3 minus lambda times minus 3 minus lambda plus 10. And when you expand the parentheses and simplify this, you end up with lambda squared plus 1. So if we want to find the roots of this, we could use the quadratic formula, but there's a simpler way to think about it. And that's that you set it equal to 0 and solve for lambda. And then when you move the 1 to the other side, you get lambda squared equals minus 1. So think about this for a second and try to figure out what happens next. Now, this is where I wish it was a real classroom so I could ask you to share your answers and we could compare. Because actually, there are two reasonable answers to this question, and it really depends on the context of the problem, what you're trying to do with it. One reasonable answer is that there are no eigenvalues, because there is no real number that you can square and get minus 1. But another reasonable answer is that there are these imaginary solutions, lambda equals plus or minus I. And if you're willing to work with complex numbers, then that's totally okay. So it really comes down to the question of, are we working with real numbers or are we working with complex numbers? Both are reasonable, and there's a lot of interesting stuff that comes up when you start working with complex numbers. Unfortunately, we're not going to have time this semester to deal with complex numbers, but it's good for you to know that this is one direction you can go farther in, and it's actually something that comes up a lot in real-life applications. So anyway, with this matrix, because it has no real eigenvalues, we would say that it's not diagonalizable. At least, it's not diagonalizable with real numbers. You could diagonalize it with complex numbers, but we're not going to do that. Okay, so far I've only shown you 2x2 examples, and so I want you to see something that has a larger matrix. So in general, this works the same. You look at A minus lambda I, and you compute the determinant. But then, because it's a 3x3 matrix, computing the determinant is a little more tricky. And so usually the way you would handle that is with a cofactor expansion. The row operation method could work, but the algebra can be a little bit tricky because you've got that variable lambda in there. So usually people will do cofactor expansions for this. And in this case, I would choose to expand in that second column because you've got those two zeros there. And so there's just one non-zero term in that expansion, and it's the term where you have the 4 minus lambda in the middle, which has a positive sign according to the sign matrix. And then when you block off the column in the row that it's in, you're left with 4 minus lambda, minus 1, 1, and 2 minus lambda. And then you can calculate that 2x2 determinant, and this is what you get. Now at this point, you might be tempted to just expand out all the parentheses, but you actually don't want to do that because the goal is to factor the polynomial. And that 4 minus lambda that's out in front, that's already a factor. So just leave that out in front and just work with the stuff that's in the other set of parentheses. And so when you expand and simplify that part, you get this nice quadratic. And that quadratic is actually lambda minus 3 squared. So in this case, there's only two different eigenvalues. There's 4 and 3. And sometimes it can be helpful to remember that it was 2 powers of lambda minus 3 in the characteristic polynomial. And so you would say that this eigenvalue had multiplicity 2. Right now, the multiplicity doesn't really change anything for us, but it can be useful to remember it for future purposes. All right, so now we have the eigenvalues. Let's find the corresponding eigenvectors. And again, the general idea is the same, but the computations are a little more sophisticated because it's a 3x3 matrix. So for lambda equals 4, we would look at A minus 4I, and here it is. And when we put that into reduced echelon form, this is what we get. And so the equations that come from this are x1 equals 0, x3 equals 0, and x2 is free because there's no pivot in that second column. And so as a vector, the solution is that x is 0, x2, 0, and you can pull that x2 out, and you get a basis vector, 0, 1, 0. And so that's your eigenvector, 0, 1, 0. All right, so let's do it for lambda equals 3. When you look at A minus 3I, this is what you get. And here's the reduced echelon form. And so the equations you get from that are x1 minus x3 equals 0, x2 minus x3 equals 0, and x3 is a free variable. And so as a vector, the solution turns out to be x3, x3, x3. And when you pull that x3 out, you have the vector 1, 1, 1. All right, but there's something interesting that happened here. If we want to diagonalize A, then we would need a basis of eigenvectors. That means that we would need 3 linearly independent eigenvectors. But we just solved for all of the eigenvectors of A, and we only have 2 linearly independent eigenvectors. So that tells us that A is not diagonalizable. And that's as far as we're going to go with that. There is kind of a next best thing which you can do when a matrix isn't diagonalizable, but that's for a more advanced linear algebra class. So there are a couple of things that you saw in this example. One is the fact that there are matrices that aren't diagonalizable, even if they have real eigenvalues. And it all comes down to the question of whether you can find enough linearly independent eigenvectors. The other thing is that for a 3x3 matrix, you have a cubic polynomial. For a 4x4 matrix, you would have a fourth-order polynomial. And in general, factoring polynomials is hard for anything beyond a quadratic. There is a cubic formula, which is sort of like a cubic version of the quadratic formula, but it's complicated, and you need complex numbers in order to understand it. And there is a quartic formula for fourth-order polynomials, but it's even more complicated. And then once you get to fifth-order polynomials, there is nothing. And so the moral is that, in general, there isn't a good way to find eigenvalues because there isn't a good way to factor polynomials. And this is actually an active area of research to find algorithms for computers to use to find good approximations for eigenvalues. And so it's kind of interesting that everything else works fine in higher dimensions. The one problem that you encounter is the problem that you had encountered before coming into this class, which is factoring polynomials.